Okay, let's get started. In the last lecture, we looked at basically a review of various types of model and model classification. Concurrently with this course, I am giving an undergraduate course on mathematical modeling, where we are going at a much slower pace, actually building the model, trying to understand the tools that are available in MATLAB. So any of you may want to also follow that lectures. Those are available already on YouTube. It's called, I think, ChE7700-L02-Computational under my YouTube channel. But this is a graduate course. We are soon going to plunge directly into algorithms and development of more advanced algorithms. But today it's going to be basically a review of linear algebra. So in the last lecture, we looked at the relationship between what I call the physical world and its mathematical representation, which we saw already as an approximation to the physical world. And the mathematical model often turns out to be nonlinear, and so we ended up developing or having a need to develop a numerical approximation to that. So this course is going to explore that link between the mathematical model and its numerical approximation. But the most important thing that you should get from the last lecture is the ability to classify the model as lumped versus distributed, steady state versus dynamic, and linear versus nonlinear. I really need to work on figuring that out. Okay. So as I said, those who want to follow additional details may choose to follow the 2176, and I have provided the link for that. Okay. So please bear with me as I get to familiarize myself with the smart board. Let me just ask the guys at PI, are you able to follow and track the changes on the board? Are you able to hear me? Okay, great, wonderful. All right, why are you laughing, Karen?
No, it's funny because they said yes.
You know, when you are using new technologies, if you are not aware that there are people outside, it's going to be a problem.
It'd be funny if they were like screaming, like typing, like, oh, we can't hear you.
All right. So the first thing that I want to point out is this idea between linear and nonlinear models, and what is our current state of knowledge in terms of understanding linear system versus nonlinear systems. So I've taken a 2x2 example here. Okay, so it's a we'll call that as a second order system. There are two state variables, x1 and x2. Okay, and I've written this as two parts. The first part consists of the linear part of it. So you can write this, for example, that part as dx as a vector, dt equals ax plus epsilon times some function. Okay, so if epsilon is small, if epsilon is 0, we get a linear system. But if epsilon is small, we get a mildly nonlinear system. But if epsilon is large, f1 and f2 are nonlinear functions of the state. Okay, so we're going to look at this problem these types of problems in greater detail. The dynamics of it, the stability of solutions of this, etc. But what do we know in terms of the knowledge that we have about such systems in the current state? Okay. So if n is equal to 2, that is, the state of the system is 2. Okay. Then we know there are analytical tools, powerful analytical tools, to study any degree of nonlinearity. Okay. So any value of epsilon or any degree of nonlinearity, we can analyze the system. Okay. Similarly, if epsilon is 0, that is, it's a linear system, then we can analyze the system of any dimension. Okay? It can be 200,000 equations, but if it is linear, we know everything about it. The mathematical tools are there for us to analyze linear problems of any size and nonlinear problems of size 2. Completely, you can characterize it completely. Okay, there are strong theoretical foundations for us to do that. What happens if we have a third order system that is nonlinear? There are no analytical tools. We need to use numerical tools to explore only in an approximate manner. Okay. So we're going to draw this diagram here where we plot, for example, n on one axis and epsilon on another axis. So if I put n equal to 2, okay. So for n less than 2, any degree of nonlinearity we know. We can understand, analyze, study the problem. For any dimension, if epsilon is 0, okay, essentially on this line, we also know for linear systems. But there is a huge space here where we know nothing. So we have to piece the puzzle together using only numerical tools. There are some analytical guides that are available, and we will see some of them, but it's essentially explored using numerical methods. Please do stop me if there are any questions. Oh, I think I'm getting better. So we're going to start looking at reviewing linear algebra in this course. Okay. So a lot of this is going to be pretty trivial. Some of them you might have seen and forgotten, but we're going to just go over the algorithms for solving. Why is linear system so important? We're talking about linear algebraic system first. Okay. So this is lumped steady state kind of models that are governed by linear equations. They are the building block for every numerical analysis problem. If you're solving a partial differential equation, what we are going to do is we are going to ultimately convert that into a set of algebraic equations. If the partial differential equation is nonlinear, you will end up with a nonlinear algebraic equation. But we don't know how to solve nonlinear algebraic equations either, analytically. So we are going to use Newton method or some sort of an iterative method to get the solution. So that is going to involve, Newton method, for example, involves solving a system of linear equations. So that is the basic building block. And so we're going to introduce the notations. So a matrix, for example, will indicate in Gibbs notation okay. Okay, by boldface A and with index notation as Aij. And the I and J will range over from 1 to M and 1 to N, for example, for a rectangular matrix. Similarly, a row vector, X, represented as Xi, I going from 1 to N, that's a row vector, Yj as an example, column vector. MATLAB has all these tools that are readily available for us to natively, intuitively construct such matrices and vectors and deal with operations on them. So what are the kind of operations that we can do? Typical addition, multiplication, division, we need to go through that. Okay. So the addition of two matrices is defined simply as A equals B plus C, symbolically. And in MATLAB, you can just type that. Once you have to find what B is, what C is, B plus C will give you A. But what does it do? What is the algorithm? What is the rule of addition of matrices? Simply element by element addition. Aij is equal to Bij plus Cij. Okay. So that means it is commutative. A plus B will be the same as B plus A, because of the nature of the definition of that addition. And it is associative. What does that mean? That means if I have three matrices, A plus B plus C, I can do A plus B first and add C, or I can do B plus C first and add A. I will get the same result. You say, well, why is he doing all this? It's trivial. It gets a little bit more difficult. But we are just setting the notations and the nomenclature straight. So what is a scalar multiplication of a matrix? So simply means that every element in that matrix is going to be multiplied by that scalar value. So K times A is equal to B simply means So whatever I show in the index notation is the actual implementation. If you're writing a code in C or Fortran, you'll have to put a loop around that. Okay. MATLAB, you can do it in loop, or it also understands the native way. So just use the same symbol that you have. So Matrix Laboratory was created to make all these operations quite intuitive and natural. What is subtraction? Subtraction is the inverse of addition. So A minus B is defined simply as Aij minus Bij, according to that. I have uploaded to Google Docs what I call a textbook that we were in the process of writing for several years ago, never got completed, but about 200 pages of material on numerical methods. I'm going to do more than what is available in there, but all these material are there, so you can also follow it from that textbook. Product is a different question. How do we define a product between two matrices? So C is equal to A times B. Okay, its actual definition is Cij is summation of Aik Bkj. Again, you know this. Okay? So it's essentially take the product of a row with a column, element by element, and add them up. Okay? So the interior index k, it goes through all the range of values. And so that is equivalent to taking, when you fix I and change k, you're taking the row of A. And when you fix k and change j, you're taking the column of B. You're multiplying each one and then adding that up. And that gives you Cij. So this has to be applied for all ij. Okay? So the matrix multiplication is a different multiplication definition than what we had for addition. Now, MATLAB also gives you an element by element multiplication if you want. Okay? But if you say A star B, it will implement this definition. But if you say A dot star B, it will do an element by element multiplication. And in fact, what this shows is that there are various needs for introducing different types of operations. We will find use for them in different situations. So all we're doing is cataloging the various types of definitions. So by the nature of this, that we have introduced the product, BC is not equal to CD. In fact, the product may not even exist when you reverse the order, because the inner dimension of B and the outer dimension of B and the inner dimension of C must be compatible. Okay, so if you have 2 by 3 and 3 by 4, you can make a product out of that, but if you change the order, then the inner dimensions won't be compatible. What I mean by that is the outer dimension here is of A is K, the inner dimension of B is K. They must have the same range going from 1 to n. Okay. So here is just an example of 2 by 3 and 3 by 2 matrix and how you do it in MATLAB. Okay, this is how you would actually enter 2, 3, 4 semicolon that says go to the next row and 1, 3, 2, and similarly 1, 2 semicolon 3, 1 semicolon 4, 1, and then C equals A times B. So MATLAB is really a very powerful tool for us to play with and learn these ideas. So all the assignments that I would want you to do would be using MATLAB. Okay? I will provide support, but if you choose to use C or any other language, you're welcome to do that. But you must be an expert in it, because I'm not. So I won't be able to provide support on any other language other than MATLAB. Now, as I said, there are other products one can define. One is called a Hadamard or a Schur product, which is defined with this symbol, a dot with a circle in the center, B. That is an element by element multiplication, which is what MATLAB introduces as A star dot. Okay? So here, obviously, A and B should have the same dimension. So here is I took the same matrices that I had defined earlier, but to make it compatible, I transposed A first so that they will have both the same rows and number of columns, and then dot star B will give you that. Now there is another definition called Kronecker product, which is indicated with this funny symbol that you see there. Okay, but what that means is you're going to take every element of A11 times B, okay, A12 times B, etc. Then we have a definition for an identity matrix, which is just indicated as I with ones on the column. This is the index notation representation of it. Why would we want to do that? We want to now explore the inverse operation of multiplication, which is the division in a number system, right? So here I'm defining I in such a way that AI is the same as I. Okay, it's like any number multiplied by 1 is the same number. So in the matrix world, identity matrix plays the same role as 1. And so you will see how that can be used to invert. So if I have a product A times B is equal to I, then B is the inverse of A. Okay, so it introduces the notion of what an inverse is. How can we look at conceptually at an inverse? An inverse of a matrix should be such that when I multiply the matrix by its inverse, it should give me I. Just like if I have two numbers, 2 times x, the inverse of x is 1 over 2. So when I multiply the two numbers, I get 1. Okay, so that introduces the notion of a division, and that's what we are going to develop. So the next, this is introducing what an inverse is, how it is defined. How do we get at it? Not only how do we get at it, how do we get at it in a most efficient way is one of the things that we are going to see today. Okay, there are conceptual ways of understanding what an inverse is, and there are computationally easy way of understanding what an inverse is. I mean, easy to understand, but not actually to execute on a computer. So one of the things that we must look at is the efficiency of operation. We must get the inverse with the least number of arithmetic operations. So what are the efficient schemes for that? And why is the efficiency become important? Simply because we'll be dealing with, when we're dealing with partial differential equations, discretization, we'll be literally dealing with millions of equations, having to invert million by million matrix. If you want to do it by direct method, it's still a challenge today. So we will see the pros and cons of various approaches to solving a system of linear equations, a large system of linear equations. Now, you can then define powers of matrices. Okay, what is A square? These are all generalizations of what we are already familiar with. A square is A times A cube is A times A times A, which is A squared times A, etc. Okay, why would we want to do that? Of course, the exponentiation, the power rule that we apply in the normal number system is also applicable for matrices. A times P times A times Q, A to the power P times A to the power Q is the same as A to the power P plus Q. That involves a lot of matrix multiplications. Okay, so it is not, for example, taking every element of A and raising it to the power. It is actually carrying out the multiplication, the matrix multiplication, repeatedly, many, many times. So we need to develop a recursive algorithm that will be efficient. But why would we want to do that? We can then generalize to functions. Okay, so we have e to the power alpha, for example. What is exponential of x or exponential of 2? It is essentially an infinite series. The way that we calculate that is by approximating that infinite series, but the definition of the function is simply 1 plus alpha square over 2, going all the way up to infinity. Now, what happens if I replace alpha by one of the matrix? Then I get exponential matrix. So e to the power a is, instead of 1, I have I, plus a square over 2, etc. Okay? So that would be an exponential matrix. Then we have the transpose defined as simply switching the indices, the rows and the columns. Okay, and that's again another definition of a new operation. And transpose applied on a sum, a plus b, is simply a transpose plus b transpose. But the transpose applied on a product is b transpose multiplied by a transpose. Okay, so those are all just quick review of the basic nomenclature that we are going to use and the basic operations on what do we mean by them. So here I'm giving you some of the special matrices. A diagonal matrix is one that has elements along the diagonal, and a lower triangular matrix, that's an important one, okay, is one which has a special structure that all the elements below the diagonal are non-zero, but every element above that is zero. Similarly, an upper triangular matrix would be one that has elements that are above the diagonal, including the diagonal, as non-zero, but below the diagonal as zero. One of the reasons why this is important, when we review Gaussian elimination, you will see that Gaussian elimination involves two steps, forward elimination and back substitution. And the LU decomposition algorithm captures essentially what Gaussian elimination does. Okay? And that turns out to be one of the most efficient way of solving linear systems. So that's the reason why we need to know what they are and how to construct them and learn about some of the properties of those. And the other commonly encountered structure would be the so-called tridiagonal system, which includes one row along the diagonal and one above the diagonal and one below the diagonal. Okay? We call this as a tridiagonal system. Now, when we develop Gaussian elimination, for example, we will recognize that when you have a special structure like that, we can tweak the Gaussian elimination scheme to stop eliminating all things that are already eliminated, that are not there, that are zero. So why spend time multiplying 0 by 0? So you won't use regular inversion methods or Gaussian elimination, but use a specialized algorithm, and that's called the Thomas algorithm. The reason that this is it occurs very commonly is because when you're dealing with finite difference, finite element approximation, you will find that a solution at one point is related to solutions on the neighboring points. Or if you're looking at the stage-wise separation in distillation column or absorption column, what happens in one stage is affecting the neighboring stages. So when you assemble the equations for those mass balance, energy balance equations, you will come across this very often, tridiagonal system. And similarly, when you're doing reservoir simulation in 3 dimensions, and you're using something called the alternating direction implicit methods, etc., you might come across block tridiagonal systems. So this is a matrix that consists of blocks, something like this, and here you will have, but in each one you will have a tridiagonal structure. Okay, so that would be called a block tridiagonal structure, and you can again develop specialized algorithms. So one of the things that you should get out of this lecture or the next couple of lectures would be the ability to write your own code for special structures that you see. In order to do that, you should understand what is the basic idea of Gaussian elimination, how is it implemented. Gaussian elimination routines are readily available, you can just download them. But if you come across any special structures, how do we modify the Gaussian elimination to take account of that special structure? Any questions? Okay, so let's look at definition of determinant of a matrix. Okay, what is a determinant of a matrix? Determinant is defined as it's called a scalar invariant, meaning it's a unique number for a given determinant. No matter what you do to the operations, changing rules and stuff like that, it doesn't change the actual value. Okay, so it is formed by summing all possible products that you can form. But the rule is you must take only one element from each row or each column of the matrix. So conceptually, if you want to state what a determinant of a matrix is, it is simply the sum of all possible products that you can form. Okay, but when you're forming, you have to form all possible products and then sum it up. Okay, and when you're forming all these products, you must take only one element from each row and each column. So if you strictly follow that, you can figure out how to calculate the determinant. Now, a mathematical way of stating that is, it is the sum of all possible products. Okay, but the products must be picked in such a way that we have only one element from each row and each column. So what I'm going to do is I'm going to fix the first index as 1, 2, 3, n. Okay, the second one I'm just calling it as L1, L2, Ln. So I have to choose that. I have to choose that in such a way that I don't pick more than one element in from any row or any column. Okay. Now this kind of definition, this is taken by the book by Amundsen, one of the very first chemical engineers to write a book on mathematical methods. I think there are 3 volumes of this. This was written probably in the 1950s or 60s. It's a very good book for introducing linear algebra from a mathematical point of view and then giving a lot of examples from chemical engineering. Okay, so you will pick, for example, L1 to be 1. Okay, then L2 cannot be 1. So it must be from the other set from 2 to n. So if you pick L2 to be 2, then L3 has to be from 3 to n. Once you have exhausted that possibility, then you need to go and say, okay, L1, because I need to form all possible products, right? So I need to keep L1 is equal to 2. Then if L1 is 2, then L2 cannot be 2. It has to be picked from the set 1, 3, etc. Okay, so it's a very tedious process to do that, but you already know an alternate way to calculate the determinant for simple 3 by 3, 4 by 4 system, which would be what? If I think I have an example later on. If you have a 3 by 3 matrix, you just take the first row or any row, pick one element, cross that row and column, because you cannot pick anything from that, and then go and form the determinant of the subsystem. And then keep applying that repeatedly. So that essentially implements this rule in a very elegant way, but not necessarily computationally efficient way. Because if you have to do that for 100,000 by 100,000 matrix, it's going to be very tedious to do it even on a computer. Implementing this algorithm, this is an algorithm. An algorithm is a rule for calculating something. So we define something and we have found out a way of calculating that, but it is not the most efficient way of calculating it. But if that is the definition, and then I give you a lower triangular matrix, and I say, okay, what is the determinant of a lower triangular matrix? What would that be? It's simply the product of all the elements on that diagonal. So it's true for lower and upper diagonal. Okay. So if I have a matrix A that I can somehow, and we will see that we can do that, split it as L times U. If you give me A, I can write it as a product of a lower triangular matrix and upper triangular matrix. That process is called a factorization. Okay. And it's like saying if you give me 10 and write it as a product of two numbers, there are many, many ways of doing that. Right? There are infinitely many ways of doing that. So the same thing is true. If you want to factorize a matrix A into a product of two matrices, there are many ways of doing it. So you have lots of degrees of freedom. And we exercise that degree of freedom to say that L cannot be any matrix and U cannot be any matrix because there are infinite possibilities. I'm saying L must be lower triangular. So I'm exercising my degree of freedom by saying that all the upper elements are 0. Okay? So if you look at it another way, this is an n by n matrix. How many equations would I have when I expand this? When I say A equals LG, what? Pardon me? Go ahead.
N squared.
N squared, right? So I will have n squared equations by equating every element on A with every element of the product. So I have n squared equations. But how many unknowns do I have? L is an unknown, U is an unknown, right? So there are n squared unknown in L and n squared unknown in U. So I have two n squared unknowns in n squared equation. So I have essentially n squared degrees of freedom. Okay. So I can use that degree of freedom to say L must have this structure and U must have this structure. Okay. If I do that, I will find, if you do the counting, I'll still be left with n degrees of freedom. And that n degrees of freedom can be exercised by specifying, for example, all the diagonal elements of U is 1. Or all the diagonal elements of L is 1. Or all the diagonal elements of L is equal to U, but I don't know what they are. Okay? So there are many ways of exercising even that last degree of freedom that you have. And each one will give rise to different names, Doolittle method, Cholesky method, etc. for factorization. And this is not the only factorization that you have. There are QR factorizations, there are a number of other factorizations that are available.
But if it exists, it has to be unique, right? If you can get LU, that's unique.
Yeah, if you agree that this is the definition that I want to get, meaning Cholesky factorization, for example, I want L to have this structure, U to have this structure, and I want L1, Lii to be equal to Uii. Then you have prescribed all the degrees of freedom. It has to be unique. Yeah, that factorization. And it turns out that for LU factorization, and we will show that later on, is able to capture what happens in the Gaussian elimination process. L contains all the operations that you are going to use in the forward elimination, and U contains all the operations that you will need for back substitution. So if you have a problem where you have AX equal to B, and B keeps changing on you, the right hand side, the forcing vector keeps changing on you, but A is same. You can do the LU factorization once, and then just multiply that by vector B. So it is essentially figuring out operations involved in forward and back substitution once, and so that makes it extremely efficient algorithm for inverting large matrices by direct methods. Let me just pause and ask if there are any questions for guys at the PI. Are you guys doing all right? Any questions? All right, great, thank you. Okay, so that's a definition for a determinant. So some of the properties of the determinant because of that are that, are you guys able to see in the back? If you're not able to see, you can log into your computer there and log into this site. You will be able to see this. You may want to test it out, because if you want to listen to the class, particularly you had some problem attending in the morning from your office, you'll be able to see the whole thing on your computer as well by pointing onto that link. Okay, so I think the computer next to you is probably already logged in. I logged in. So the determinant of a diagonal matrix is simply the product of all the elements in the diagonal. Similarly, the determinant of a lower triangular matrix is simply the product. The reason for that is, if you take all the other elements that you must add, but they will always get multiplied by a 0 on the other side of the matrix. Okay. And if every element of a row, for example, gets multiplied by k, then that is the same as k times the determinant of A. So replacing any row or column of a matrix with a linear combination of that row or column leaves the matrix unchanged. So that's why we call it an invariant of the matrix. So the consequences of rules 3 and 5 is that if two rows of the matrix are identical, then you can subtract one from the other and replace it, and you will get a 0. So if you have a 0 in an entire row, the rule that says that you must pick one element from every row will get a 0 multiplication of every term in the summation. So the determinant is 0. When the determinant is 0, we call that matrix a singular. Then we get into all kinds of problems. We cannot invert the matrix, and those are the singularities that we will talk about. There are interesting things happen in the dynamical sense of the equations. So if you change any two rows, then the sign of the determinant changes. Again, you must have seen these in linear algebra. I'm just trying to draw back attention because we'll be using some of these later on. So another algorithm, which is in fact the one that you would implement by hand if you're using it. It has a special name called the Laplace expansion of the determinant. So it's essentially summation over any row or any column. So take a row, and you have to sum all the quantities on that row. So take that element, okay, and multiply it by its cofactor. That is, by crossing out that row and that column, whatever is remaining, you find the determinant of that according to this. Okay. So that's a process that recursively is applied to get the determinant. It's another way of implementing the same idea. Okay, so we will use this to develop something called a Cramers Rule, and then we will see how that leads to an algorithm, a recipe for inverting a matrix. We saw what an inverse of a matrix is. If you give me A, I need to find a matrix B, which when I multiply it by A gives me I, but I don't know still how to get B. Okay, so that's one of the things that we will develop by looking at this in a conceptual way. Here is just an example of the Laplace expansion. So you have a 3 by 3 matrix. So you take, for example, 1 here and multiply it by what is left after crossing that out. Okay, and then you do the same thing for the second term, which is 0, multiplied by what is left, which is 0.702, etc. And the third term, 0.306, multiplied by what is left. And the nice thing is MATLAB has a built-in routine called DED that takes any matrix, but you cannot really challenge it. If you give it 100,000 by 100,000, it will hang for a long time. Okay. So it's a good tool for experimenting with these ideas for small matrices and learn. Now again, Cramers Rule. Is there anybody who has not seen what a Cramers Rule is? Might have forgotten it, but you must have seen it in earlier courses. So if I have a 2 by 2 system, I'm just illustrating what the idea behind it is. 2 by 2 system, and I'm eliminating the variable x2 using Gaussian elimination. Okay, that simply means I'm going to multiply the second row by, for example, 1 over a12, a12 over a22, and then add it to the first one. And by linear combination of this, I will get this equation after I eliminate x2. So I have only x1 in here. Now, what I'm trying to look at is a pattern that I can generalize from 2 by 2 system to 200,000 by 200,000 system. Okay. So what do I have here? I have on the right hand side a product a22b1 minus a12b2. But that is the same as the determinant of a new matrix that I construct from A, where I have replaced the first column by b1, b2. So I'm going to indicate that as A parenthesis 1. So this matrix A1 is a matrix, original matrix A with one change. And that change is in column 1, I have replaced it by the forcing vector. And then I calculate the determinant of that. Okay? And that is the determinant here, which is the same as the right hand side that you see here. Similarly, on the left hand side is the determinant of the original A. Okay? So x1, so the left hand side is the determinant A, and the right hand side is determinant of a new matrix A1. So x1 is simply A1 over A. So x1 is A1 over A. So if I have an n by n system, this gives me a way of an algorithm. If I have a function that can calculate the determinant, then by repeatedly calculating n plus 1 determinants in total, I can construct the solution vector. Okay, x1 to xn. That means I need to calculate the determinant of a1, where I replace the first column with b, then ak, which is the kth column with b, and in every case I divide this by determinant of a. Now you can begin to see why when the matrix A is singular, we don't have a solution, because we have division by determinant of A. Okay, so if the determinant of A is 0, then there is no solution. So that is Cramers rule generalized, but it is not an efficient rule. Why? Because calculating the determinant is a computationally intensive task using the algorithms that we have seen so far. Okay, and if you have to do that n plus 1 times, then it becomes a fairly demanding computational task. Okay. So we already saw conceptually what an inverse is. Okay, an inverse is such that if I multiply the two matrices, I should get the identity matrix. So A is given, B is what we want to find out, and B is what we call the inverse of A. Okay, so we take, for example, the Laplace expansion, the definition for Laplace expansion, and Cramers rule. We combine these two. Okay. So the Cramers rule tells me how to calculate x1, xj, xn. Okay. It's simply the determinant of a1, which I expand here. Determinant of ak in general is like this, where the kth column is replaced by b. So for x1, the first column is replaced with b. Okay. And jth one, the jth column is replaced with b, etc. So that is the Laplace expansion, and this is the Cramers rule. By combining these two, I have obtained the solution for each element of that vector x. Okay. So now I can write this set of equations. I have n equations in here. Okay. I can write that as a vector matrix product. So on the left-hand side, I have this vector x1 to xn. Okay, and all of them have the determinant of a as a common factor. So I put that as the, and it's a scalar number. Okay, and then if I look at what is left, they all have b1 to bn. Okay, so I can collect that as a vector, b1 to bn, and arrange the remaining elements as a11, a21, an1, etc. These are the cofactors that have come from the Laplace expansion. So each one is actually a determinant of a submatrix. So if it is a11, I have to cross out the first row and the first column, take that remaining in A and calculates its cofactor according to the definition. So it is, and if you see the order of the indices, you will find it's a11, a21, etc. So it is the transpose of the matrix that you will find. So now I have the rule, because I can calculate everything on the right hand side. I can calculate the determinant, I can calculate all these elements in here, right? So x is equal to something times b. What is that something? That is the inverse. Why is that the inverse? Because what we are doing is we are solving this, ax equal to b, right? But what I have done here is I've written something like x equaled some matrix b times that vector b. So this entire thing that you see here, okay, is my b, and that is the A inverse. Okay, so I have developed or discovered a formula, a recipe that I can implement, I can program, that will give me what each element of that inverse matrix is. Okay, so the combination of Cramers rule and Laplace expansion gives us one way of getting what that inverse is. So we saw conceptually what an inverse is. Now we have a computational algorithm. Again, this is not a very efficient algorithm because calculating determinant is a computationally intensive task. Any questions? Yeah, that's what we're talking about. X equals matrix B times B, but the interpretation for B is that it is A inverse. Okay. So in some linear algebra books, you might be introduced inverse as the adjoint of A divided by determinant of A, where adjoint of A is this entire thing for you. Okay. Now, what is the inverse of a diagonal matrix? Remember, the definition of an inverse is that when you multiply it by the inverse, it should give you identity matrix. Okay, so the D inverse is simply 1 over D11, 1 over D22, etc. That's a very simple algorithm for finding the inverse. Okay, so that's what you need to do. You need to look for more efficient ways, understand what the concept is, and then know. At this stage, you don't really have to code these things because they have been worked on for so many years, and there are lots of very efficient codes available. So you should be able to search for which one is efficient and why it is efficient. That will fit your needs. Now we get into some of the more interesting, finer points of seeking efficiency in inverting a matrix. So inverting a general matrix is still a computationally challenging job for large sizes of matrices. So is there an efficient way of inverting a triangular matrix, for example? Okay. So if U is an upper triangular matrix that is given to you, and your job is to find its inverse B. B is equal to U inverse. What kind of ideas can be used to find a very efficient and a very simple scheme that we can program ourselves? So the way I'm going to start this is by saying, okay, U is given. I'm multiplying it by please bear with me because this smart board is too smart for me. So I'm still trying to learn the final points of this. So I'm introducing this, and I need to find every element in that. I don't even know to begin with whether it is going to be also upper triangular. Okay, so I'm going to use the logical way of constructing what it is. But what I know is when I multiply this 2, I must get I. Okay, so this is known, and that is known, and this I need to find out. Every element in that. Okay, so the first thing I claim is that that is also going to be upper triangular. That is, all the elements on the lower triangular are going to be 0. You have to sequence the calculations. That is the key. Okay, you have to sequence the calculations in a certain way so that you develop the most efficient algorithm. You can pose this as, again, okay, I have n square equations, right? This is an n by n matrix, so I have n square equations by equating each element, and I have n square unknowns. So I can write down the n square equations and then try to solve for that. That really doesn't help because I have enlarged the problem from n by n to an n squared by n squared problem. So if I'm clever enough and sequence the calculations, I can figure out all these n square elements with a very few simple steps, 3 or 4 steps. So first, for example, I take the product of, I'm not sure how I'm going to do this. Okay. Let me take the product of this row with this column and set that equal to that number. Okay, that's what that definition is, right? So what will I get? 0 times V11, which is 0, right? So every term here gets multiplied by 0. These are all given to me. So the very last term is UNN times VN1 is equal to 0, right? But UNN cannot be 0. What happens if any one of these is 0? The diagonal element is 0. You get a determinant as 0. It's singular. It's not invertible. So you cannot do that. Okay, so you have to assume that this is a non-singular matrix, so none of the diagonal elements are 0. So UNN is not equal to 0, so VN1 must be equal to 0. Okay, then you go to the upper one. Okay, and then take the product with this. I have to use a different color. So I take this and this. So once again, I will find the same thing. 0 multiplied with this, 0 multiplied with this, until I go to UN minus 1. So UN minus 1 times Vn minus 1, 1, plus UN minus 1n multiplied by 0. Right? Because I have already discovered that the last element is 0. But if I started off with this equation, I would have 2 unknowns in that equation. Both Vn minus 1, 1 and Vn1 will be treated as unknowns. Okay? So it's essentially to sequence the calculations in this particular order to show that every one of those elements are 0. Once you have figured that out, then go to the next column here and start the same way. And you will find that you can show that all the elements on the lower part of this matrix is equal to 0. So once you know that, you don't even have to write that or code it in any of your program because you already know that it is 0. Okay? So then what do? We start developing in a similar way, to find out what are the diagonal elements and what are all the upper diagonal elements. In here, you need to be very careful to sequence the calculations, alternating between one row from here and one column from there. And if you sequence that, you will not have more than one unknown at a time. Remember, there are n square unknowns here. There are n square equations. So it is just the trick of sequencing it so that when you are writing an equation, that equation has only one unknown at that time. All the other variables that are appearing from V in that equation are known from previous operations. Do you understand the idea? I just want to convey the idea, but you need to kind of lock yourself up for half an hour and write it out to really register it in your mind. Okay, I can show the path, but it won't register in your mind until you do it by, and I did it when I was a graduate student, and that's how you internalize it. Okay. So here is the key. I myself forget the order, so I'm just reading it here. Okay. So for each of the diagonal elements of I, okay, summing the product of each element of the ith row of U for the corresponding element from the ith column of V. Okay, and that's fairly, because once you've seen it, it's fairly easy to understand. So what we are saying is the next thing, after establishing that all the lower elements are 0, try to establish all the diagonal elements. Okay, so if you go to this row multiplied by that column, so you will get U11 times V11 plus U12 times 0, because you already established that. So all the other elements gets multiplied by 0. So U11 times V11 is equal to 1. Okay, so V11 is 1 over U11. So you do the same thing, the second row with the second column, third row with the third column, etc. So you'll find all the diagonal elements from that. Okay, so that is one key equation which tells you all the lower diagonal elements, and you don't even need to program that, but you do need to program this. So every equation that you need to program, I put it in a box. So VII is equal to 1 over UII. So you need to set up a loop, and I will show you the MATLAB implementation of this soon, over all the n. Okay, so you find all the diagonal elements of VII. And for each upper elements of ij, summing the product of each element of the ith row, the corresponding element of the jth column. Okay, so this equation you really need to see both the pictures, the symbolic representation, the expanded representation of the matrix. So what we are essentially saying is, I'm going to take one row from here and one column from there and write out the product in detail. Okay, so if you take, for example, the first row with the second column, we'll have U11 V12 plus U12 V22. That's it. Everything else will be 0. Okay, and in that one you will have only V12 because V11 we already found out. Okay, so just scan across that and write down an equation and extract the unknown to the left hand side from each one. And that is the equation for a product of one row with one column, one row from U and one column with V, and in that you extract this Vij term. Okay. Move everything else to the other side. So once again you have 1 over Uii. So the diagonal elements cannot be 0 because you are dividing it by this. And the key here is to figure out this range of indices. How do you have to do? You have to do it in the order of j going from 2 to n on the V matrix, and j must always be greater than I. Why do you think that is so? Because you're looking only at the upper part of it. Okay, and then I going from j minus 1 to 1. Okay, and that's all the algorithm is. Okay, so essentially there are 2 steps. I think this is one step, but there are 2 loops inside this, and then the other step for the diagonal elements that we wrote with just 1 loop. Okay, I think I might have written a MATLAB code for this, which I called a naive implementation of it. Okay, so you give me U, and I find out what the size of that matrix is, and then I initialize V to be zeros n by n, and then the first loop, which implements the diagonal elements, finds all the diagonal elements. And the second equation has 2 loops, and that's all. Very simple code will find the inverse of any size upper triangular matrix. Okay, that's what I mean by efficiency. And I would like you to kind of play with MATLAB and test it out. Here, what I'm showing is I'm defining a 4x4 matrix. Okay, and the tick and talk function give you the clock time for execution. So the in U is the function that I wrote here, and in is the general function that MATLAB has built in. Now, what is the difference between these two? The in function does not treat any special structure. It treats U as a general matrix. So if there are zeros, it's still going to eliminate the zeros, and so it should involve more floating point operations than what I have implemented. Okay, so test it out and tell me what you find in the next class and why it is. I want you to think about it. Okay, so what would you expect if I ask you which one should take less time? The function that we wrote in view, or the function built in n? Any ideas? You would think that the one that we wrote is more efficient, right? Because it takes into account the special structure. It doesn't find all the, doesn't do operations with all the zeros to get rid of them. That should be true, right? But the function I and V, you will find when you run this, runs faster than this.
Because it's vectorized and it's also written in C. Yeah, there are reasons.
He has all the right ideas, and I want all of you to get all those right ideas. That is the reason that this function I and V beats the function that we have written, even though it does more. Like at one time, 10 years ago, MATLAB used to have, instead of tick-tock, it used to have flops. There's a function called flops, which stands for floating point operation. So it will actually tell you exactly how many floating point operations was carried out by that particular command, by that statement. In order to do that, they have to actually count every multiplication. So it was a very heavy load. Initially, MATLAB came as an instructional tool. So it was a very useful tool to have. But then they went into the commercial side and wanted to make it more efficient. And one of the things to go out was the flops count. So all you get now is the clock speed between the starting and ending of the particular command. But the in function is highly optimized and compiled. One of the things that you should know about MATLAB is that it is interpretive. How many of you know the difference between interpretive and compiled? How many of you have written a program in C or Fortran? Only a few. So an interpretive language, like MATLAB is called an interpretive language. It has a great, basic is like that. It has a great advantage in the sense it interprets as you type. So it makes it interactive. So you can type a command and it says, okay, what is it trying to say? That's the interpretation process. So it has to decode what you have written, convert it into the machine language, and then the machine executes that. The machine language depends basically on the processor. The CPU has a set of assembly instructions that you can understand. So this has to convert that, and MATLAB interpreter does that. Whereas C, Fortran have a compiler. So it's a two-step process. You write a program, and you pass it to the compiler, and the compiler compiles it and produces something called a .exe file, an executable file. And that's a machine-readable file. So you execute that, and that runs much faster because the compilation step has been done once and for all. Now, all the MATLAB built-in functions, sine, cosine, exponential, inverse, those that are computationally intensive, they have optimized it and compiled it and made it available as a library. Okay, so when you're calling in, it actually calls the binary library, and it runs extremely fast. So in the clock speed comparison, you don't see it because it runs much faster than what we have done. But in the floating point comparisons, I have this, I think, in the notes, because the notes was prepared 10 years ago. This will come up with a floating point operations of about 125 or something. This will come up with a floating point operation of 55 or so. Okay? But still, this will run slower than this because there is load on interpreting this. Now, if you have a loop, and this particular line has to be interpreted every time it goes through the loop. Okay, and that's a tremendous load on any interpretive language. Okay, so it's MATLAB, and any interpretive language is great. Python, those are all you can type. It's interactive and it's interpretive, but not necessarily computationally efficient. So MATLAB has come up with a solution for that, and that is you can take the programs that you write and you can compile, and you can produce an executable. They call it MEX file, MATLAB executable file. Okay, so to make it faster.
That code would run a lot faster too if you vectorize. Are you going to talk about any of that?
I'm not
like
going to get
loops
it.
are really slow in MATLAB because, like you said, it has to interpret every line.
Right.
But you can actually go in and vectorize it using the slice.
Right. I'm not going to talk about MATLAB per se in this course because the focus is on algorithms. I'm just illustrating in a few cases how you would implement the ideas, because otherwise it remains as an abstract idea. We talked about it, these are the equations. Okay, now I have a code. You can actually see how it is implemented, and in your assignments.
Explain it in the help file. So if you run into, I guess my rule of thumb, what I've picked up over the last 3 or 4 numerical courses I've taken is I don't use a for loop in MATLAB if I can ever help it, and I can vectorize it.
Yeah. Like here, for example, I have used a vectorization operation.
Yeah, see right there.
Okay,
Yeah.
so this is a vector multiplication of that portion of u with that portion of v. So I still have to select that portion of u and v from the memory, and then I could have put an element by element multiplication and a summation to multiply a row with a column. Okay, so here I have used the MATLAB vector multiplication. So whenever you can do that, you should. Now you should then also see whether I can get rid of this for loop and put that also as a vector matrix multiplication. That will speed up your execution. It does not reduce the number of floating point operations. Okay, that is determined by the algorithm. You have to do so many operations, but how can you do it in a vector form or in a parallel form when you have multi-cores? And these are really, a computing science course will address more on the architecture of the CPUs and how you can implement these algorithms in a most efficient way. That's a vast research area by itself. Any other questions? One request I will have for you is just don't come and listen and go away and come for the next lecture. You need to put some time in between reviewing what we have seen and thinking about some of these things and trying to write your own code. I'm not going to force you to do a lot of this. I'm going to have probably 4 or 5 assignments and then a major project. Okay? So the project will actually expose you to computational transport phenomena. That's my goal. Okay? We are going to get to the stage where we understand all these algorithms and we can use COMSOL, which Mrinal will introduce pretty soon, to solve realistic engineering problems. Okay? So it's not a computing science course in that sense, but you should develop some appreciation for what the algorithms are, why a certain algorithm is more efficient. When you're using COMSOL, you will have an option for your linear solver. Do you want to use a direct method? Do you want to use a iterative method? Among iterative method, you may have options of GEMRIS, conjugate gradient. What do these things mean? Okay? That's my purpose in the lectures, is to expose you to those terminologies and the ideas behind them. Okay. Now, Gaussian elimination. I just have one picture just to talk about, again, I think you have seen this, but to illustrate how the process works and what does the transform matrix contain and how is it related to the LU decomposition. Gaussian elimination is one of the bread and butters of solving system of linear equations. The most efficient general purpose method, okay, for solving a system of linear equations AX equal to B. Okay, so you are given a matrix A that you see here, okay, and you are going to augment that with the vector that you are given. So you are going to construct a new matrix which is going to be n rows and n plus 1 columns, but the n plus 1 column will be your matrix B. Okay. Now, if you have two systems, vector B1 and a vector B2, you can stack them up as B first column and the second column. Okay. So why you can do that is the same matrix A is going to be used to solve both the problems. So the operations of eliminations are the same. So in one go, you can get the solutions for both problems. Sometimes what would happen is you have the forcing function that depends on the vector itself. So you have to do it sequentially. In that case, if A still doesn't change, that's the time when you can factorize A into L and U, so that you can apply the back substitution very easily to get the updated solution for every case. So what is the idea behind Gaussian elimination? We want to eliminate all the elements in this column. That is, we are eliminating x2 to xn from all the, we are eliminating x1 from equations 2 to n. We are eliminating the variable x1. That means we are making these as zeros. Our goal is to make these as zeros. So we need to figure out what kind of operation we need to do, okay, so that we can code that. So I've shown you the MATLAB piece of code for every kind of operation that we need to do. So let's look at this. So what we are doing is we are making the first element as 1. So we need to find out what I need to do to make that first element into 1. I need to divide every one of them by A11. Okay, so this is A11. I'm dividing every one of them, that row, by A11. So I figured that out. So I figured out that range j going from I plus 1 to n plus 1, Aij equals Aij divided by Aii. But that piece of code is going to be embedded into another loop, and that loop is here. Oops. I still haven't mastered this. Okay. So what we are saying is, okay, I need to eliminate x1 the first time, and then I need to eliminate x2 in the second step, and x3 in the third step, and I need to continue that. So I put an outer loop which is going to repeat this loop for every row. Okay, so by the time I'm finished with this loop, what I will have is I've eliminated all the elements in the lower part of that matrix. I've made them to 0. Okay, so that is my goal for this outer loop, and within the outer loop I have several steps. The first step is to make the diagonal 1 by dividing this. Okay. And the next step is to make all these elements as 0. So I need to figure out what operation I need to do that. Okay. So I need to multiply, that is, I take A22 and subtract from A21 multiplied by A12. Okay. So when I do that, this becomes 0, and that will be changed. Okay. And the new numbers will be put in its place. So this is a new number in its place. So whenever you see a product, the cross above, that means that number has been changed by that particular operation. Okay, so already after the second step, you'll find all these elements have been changed. They are stored in the same location. Efficiency of storage is important. Efficiency of computational speed is important. Okay, so we are not creating a new matrix. We are storing in the same matrix, but the numbers have changed. I've lost the original number now. Okay, and then this operation is the one that's going to, and this is why I said you need to spend some time trying to make sure that you understand each piece of code, the logic behind it. Okay, so that code is going to change all these numbers, but the purpose of that code is to make this 0. Okay, and that is going to be embedded in another loop, which is going to make every one of these elements in the first column 0. Okay, so it's a loop within a loop, but there are only a few statements, few commands. This is one command, that actually computational one, and this is another one. Okay, but it's just that it's cleverly embedded one inside the other, because the same idea is repeated after you eliminate the first variable x1 from all this. Just go back and repeat that calculation and that calculation for every one of the other variables, x2, x3, x4, etc. And at the end of this process, we end up with a matrix that looks like that. It's an n by n plus 1 matrix, but all these elements have been changed to a new number according to that formula. If you understand everything that I have said, I've given you the original matrix. I started with the original matrix. I've done all these calculations. I'm going to ask you a question. What will be the number that is stored here? Zero? So now I'm asking you to kind of think, not just listen. I was given a matrix A and a vector B, and I formed this augmented matrix, which is n by n plus 1, with the n plus 1 column being B. Okay? And then I figured out all these operations, and I have carried out these operations. Watch out carefully. In this operation, I go from j equals I plus 1 to n plus 1. Okay? That is from the next one, because this is already 1. Okay? This operation, that operation will make that element 1. But will it actually store 1 there? I have not touched that element in that calculation. Okay? So whatever is below, I know that it must be 0 and 1 on the diagonal. But because I know already, I don't explicitly calculate that. So none of these calculations here actually calculate that particular elements below the diagonal or on the diagonal. Okay? But we have figured out all the operations that are necessary and stored them on above diagonal. Okay? That's very important to understand that if you look at the matrix and print it out, you will find some garbage number there. Maybe the same original number because they're never touched. But you're not going to use that. Okay? You're just going to use only the upper part of that for the last step, which is the back substitution step. So the forward elimination step gives you an upper triangular matrix. Okay? And the operation that is necessary to get there, this is the most efficient implementation of that operation. But there is another way of looking at it as a LU factorization. Okay? And we will show that later on. Now, the back substitution, this is the starting point of the matrix, and that's fairly easy to understand. Because in the very last equation, you have 1 times xn is equal to a(n)n plus 1 when you do the vector matrix multiplication. So xn is simply this number. The last solution, the last element of the solution vector is just this number. Okay? And that is the one that you will have. And then when you go back, you have to go back in this way. So there is a loop that you will see here that goes, it's a back substitution. It goes from n minus 1, in steps of minus 1 to 1. Why do you do that? Because that way you will have only one unknown at every step. Okay? And then you go to the previous one, it will have 2 terms, but one of them will be known. The last element of the vector will be known. So there will be only one unknown vector, unknown element of the vector, and you can just substitute. And the solution finally will be stored in this column. You put B in there and you get back the solution vector in that particular column of the matrix. I call it as a naive Gaussian elimination. Why did I call it as a naive Gaussian elimination?
Because it may or may not work.
Hmm?
It may or may not work.
It may or may not work. When would it not work? That's a good point. It won't work sometimes. Because understand what elimination is, I have developed an algorithm that will work. Okay, it should work, except there are situations where, yeah? Did somebody say? This process of calculations of elimination could result in a number that is very close to 0 on the diagonal. You're subtracting 2 numbers, for example. There are a lot of subtractions in here. Okay? So when that happens, it does not necessarily mean that the matrix is singular. Okay, so as you are carrying out the elimination process, if you get into a situation where the diagonal element is a small number, it will never be zero in a finite precision calculation. It will be a small floating point number. Then you are dividing by that, and it increases the error. Okay, so at that stage, a more clever implementation of Gaussian elimination will say, I'm going to switch that. I'm going to push that to the last row and bring an equation from below to that level. That is called pivoting. Okay, so often you will find in direct methods you have to specify a criterion on when to use the pivoting. If the number is less than 10 to the minus 7, 10 to the minus 8, you might say invoke the pivoting algorithm. Pivoting algorithm is essentially nothing but switching two rows, and that doesn't change the problem, but it makes the algorithm stable. Okay. If you continue to pivot like that and you end up with a number that is very small in the last one, what does that mean? Then it means that you have a singular system or nearly singular system. Okay. The other thing that you need to notice is these are called direct methods in the sense that you get a solution in a finite number of operations. Okay, you can count how many floating point operations you will need to get the solution. And whenever you have a multiplication or a division, there is always an error that is introduced. That is called the round-off error. Okay, like 1 over 3, for example, is never represented. It is 0.3333 forever. Okay, but you are going to round it off at a certain number of decimal places. If you are doing in double precision, approximately 14 decimal places. So when you have numbers that are already have error in them, and when you carry out products with them, it's going to propagate that error. So direct methods are prone to round-off error propagation. That is, these errors accumulate. And if you have a million equation, then the error can overwhelm it and you get absolutely nonsense at the end. So that's something that we need to watch out. One of the disadvantages of direct methods is the inability to get rid of the round-off errors. Whereas iterative methods are very good at that because they try to get rid of any error. You provide an initial guess which is a huge error, and the method is constructed in such a way that it reduces the error, it eliminates the error. So there are some clever combinations of iterative and direct methods. So you get a direct method first, and then you apply a few iterative iterations on that to improve your accuracy of the solution. So this is the MATLAB code for the naive Gaussian elimination, and I want you to again study that. That's why I put it here. And essentially, I am putting on n plus 1th column the vector b. I need to pass a and b. A is the matrix and b is the vector, and it's going to return the solution vector x. Okay. So I have a few error checks, and then the first step is to form the augmented matrix, and then I have step by step, steps 2, step 3, step 4 that I've identified. So it's really not a very large program. Okay, just a few lines of code. It does not include pivoting. Okay, and that's why I call it a naive scheme. So it'll work as long as you have a well-formulated problem that doesn't give you zeros along the way during elimination. Now, the loss of accuracy. This is the idea behind pivoting. Maybe I think we need more than 2 minutes to go through this. So we will stop here and continue with this in the next class. Okay? Thank you. So, was there any problem for you guys at CI? Were you able to listen to the whole thing and see what is happening? Was there a lag in transmission and things like that? Thank you, Rashid. How about others? Are you all in the same room or in different places? Yeah, thank you. Okay, great. So next Monday then we will see you. And okay, great. All right. Thank you very much.